Present in the other classes that were taking place?
No.
It is okay. So we'll be looking at mole concept. Have you covered mole concept before?
At my former school, not yet.
Not yet, but you covered it in S4, right? S3 and S4.
Yes, we did.
Okay, so we're going to remind ourselves with just a video, some videos, and then I'll share with you the unit. I've looked at in the course that we have on the website. I think I need to make a new one with some things that I need. I need to update. So I'm going to take some time to update the entire notes that we have on the website so that you can access very updated notes. The ones we have right now are not really to what I wanted them to be. But nevertheless, we shall we will access them, and then you can utilize them as I also update what I want them to be. But for now, let's see this first video about mole concept, and then we can see how to continue from there. Let me make sure I share my sound. Let me know if you can hear well.
They are, and we're going to talk about some of these important numbers.
Can you hear the sound?
Yes, I'm getting the sound very well.
Okay. So do you have where to summarize down some things?
Yes, I have.
Okay. So when you reach somewhere and you're confused, just let me know. I'll pause and then explain, okay?
Okay, sir.
Numbers and terms. Now we're going to start from the very beginning on moles here, so no matter how much you know or how much you don't know about moles, this video will be a great place to start. So what's a mole? I'm not talking about the cute little furry creatures that live underground here. I'm talking about the kind of moles that are super important in chemistry. So a mole is a name for a specific number of things. Okay? A mole is kind of like a dozen, right? A dozen is the name for 12 things, or 12 things in a dozen. Now a mole is like this, but it's way bigger than a dozen. 12 things in a dozen. In a mole, there are 602 hexillion things. This is 602 followed by 21 zeros. 602 hexillion things. So a mole, like a dozen, is a name for a certain number of things. There are 12 things in a dozen. There are 602 hexillion things in a mole. This is a gigantic number. Now here's one thing that confuses people about moles. They forget that a mole is a name for 602 hexillion things, and they think that a mole is an abbreviation for the word molecule. So many people think this. They see mole and they think, oh, you mean molecule. No, no, no. If I write mole, I don't mean molecule. I mean a group of 602 hexillion things, not a molecule. So there are 602 hexillion things in a mole. And just like a dozen, we can have a mole of anything, right? So we could have a dozen donuts, which would be 12 donuts. Or we could have a mole of donuts, which would be 602 hexillion donuts. Or hey, we could have jelly beans. A dozen jelly beans would be 12 jelly beans. And a mole of jelly beans would be 602 hexillion jelly beans. So sometimes people get freaked out about moles, but just remember they're a lot like a dozen. 12 things in a dozen, 602 hexillion things in a mole. You can have a mole of donuts, you can have a mole of jelly beans, a mole of cars, a mole of paper clips, a mole of bouncy balls. Just as long as it is 602 hexillion things, you got a mole. Now let's talk a little bit about this actual number, 602 hexillion. This number is often referred to as Avogadro's number in honor of the Italian scientist who discovered it. But now, check this out here, right? 602 hexillion, this is a gigantic number. 602 with 21 zeros after it. Think about what a pain it is to deal with this number, right? If you're doing math by hand, you got to write this out and like do your multiplication and division with 21 zeros. Even if you're using a calculator, you got to type in all these zeros and make sure you have the right amount. And then when you get your answer, you got to go back and count how many zeros your answer has. It's a total pain. So instead of writing out 602 hexillion with all these zeros every time we want to talk about moles, we tend to abbreviate this number. Now, as you may know, when we abbreviate numbers in math and science, we usually use a technique called scientific notation. And here's how we would abbreviate this number using scientific notation, okay? I got this big number, 602 hexillion. I find out where the decimal place would be. It would be right here. And now I move the decimal place until I have just one digit to the left of it, okay? And I count the number of spots. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And now this is my new spot because there is a 6, just one digit to the left of it. So I moved my decimal place 23 spots to the left. And that means that in scientific notation, I would rewrite this number as 6.02 times 10 to the 23rd. The 23 comes from the number of spots that I moved it to the left. So 6.02 times 10 to the 23rd is how we often abbreviate this gigantic number, 602 hexillion, when we want to write it out and use it, say, in math problems. Now, this is a convenient way to write this gigantic number in scientific notation, but it's also a terrible way to write it, because this number, 6.02 times 10 to the 23rd, it looks terrifying, right? It's got this 10 with the exponent, 6.02 times this thing. It's like people see this number and they're like, oh my God, what do I even do with this? Relax. It's okay. 6.02 times 10 to the 23rd might look a little terrifying, but just remember that it is an abbreviation for 602 hexillion, that it is an abbreviation for this very large number here. And every time you see 6.02 times 10 to the 23rd, just remember that it is an abbreviation for 602 hexillion. Okay, so now we've learned what a mole is, how many things are in a mole, and we've learned how we can abbreviate this gigantic number, 602 hexillion. The last thing I want to do is give you a sense of how gigantic this number, 602 hexillion, how gigantic it really is. Okay? So let's think about this mole of jelly beans that we talked about earlier. 602 hexillion jelly beans, which you know now we can abbreviate as 6.02 times 10 to the 23rd jelly beans. These are all just 3 ways of writing the same number. Okay, if you had 602 hexillion jelly beans, that would be as large as the entire planet Earth. A mole of jelly beans would be as big as the planet Earth. That is crazy. Think about how many jelly beans that is. I mean, really, think about how many jelly beans it would be if your house were filled with jelly beans. Okay, that would be gigantic. Think about how many jelly beans it would be if every building in your town was made only of jelly beans, okay? Like, that would be a ton. Now, imagine how many jelly beans you'd have if the entire Earth were made of nothing but jelly beans. And that is how big a mole of something would be. Now, we could have also a mole of donuts, which would be 602 hexillion donuts, 6.02 times 10 to the 23rd donuts. If we had this many donuts and we stacked them on top of each other like this, and we had 602 hexillion donuts and we kept making this stack would reach from the Earth to the sun and back 200 billion times. This stack of donuts would reach from the Earth to the sun back and forth 200 billion times. Again, think about how many donuts we would have if we just laid donuts down like this from like your house to your school, right? That would be a ton of donuts. Now imagine going from Earth to the sun and back 200 billion times. That is how many donuts 602 hexillion donuts is. But now here's the thing, this is really interesting. We're talking here about jelly beans and donuts, but a lot of times in chemistry, we're talking about things that are much smaller. We're talking about atoms. Now, a mole of jelly beans would be as big as the planet Earth, but a mole of atoms is much smaller. Here, in this container, I have just about 1 mole of sulfur atoms. This yellow powder and these yellow chips are made entirely of sulfur atoms. And there are about 602 hexillion sulfur atoms in this little dish here. So think about this, right? Got 602 hexillion sulfur atoms right here. Now, 602 hexillion jelly beans would be the size of the planet Earth. 602 hexillion sulfur atoms can fit in this little dish. This shows us how absolutely tiny a sulfur atom is, how tiny all atoms are compared to a jelly bean. Really, a mole of these is the size of planet Earth, but a mole of these little sulfur atoms can fit in this dish. So when we're dealing with something as tiny as atoms, a mole doesn't actually take up that much space because the things that we're dealing with are so incredibly small that a giant number of them just isn't that big. So just to review what we've talked about.
So Emily, do you understand what we're talking about here? We're just trying to explain how big a mole is, or the size of a mole of a substance, any substance. Okay, I think Iranya has also joined us. So the way we explain a mole is just a representation of a number. The number that you've seen that we call the Avogadro's number. This Avogadro's number is so big that we can't always keep on writing it. So what we do is we just abbreviate it. By abbreviating it is using the scientific notation, where we get 6.02 times 10 power 23. Okay, so that's the abbreviation. But if you don't want even to write that number itself, you just have to write 1 mole. Okay, 1 mole represents that number. So if I say 1 mole of sulfur, like the way they're saying in the video, we are saying 6.02 times 10 power 23 atoms of sulfur, that type of thing. Okay, that's what we are meaning when we say 1 mole of sulfur. Okay, so that's the mole. It's just a number that we try to abbreviate to make sure that it is understood. Now, this number can be any other number, but as a scientific community, they chose that number 6.02 times 10 power 23. And it doesn't have to make any difference the moment every scientist out there is using the same number. So that's it. That's what a mole is. Do you have a question? Emily, do you have a question, or Iranya?
No, sir, everything was clear.
Everything was clear. What about Iranya?
No question, sir.
Okay, Iranya, were you around in the last few weeks when we were conducting free classes?
Yeah.
So we studied this, not so?
Yeah.
Okay, good. So we're just revising to see that we are prepared for the activities that we shall be doing as we continue with this engagement. So I'll send out to you an activity to do about mole concept. But so far, this is all we have looked at: the mole, Emily, I also send you videos to the lessons that we had. I think I can gather those. They're on YouTube. You can always access them. I'll send you the links after here so that you can access them and see the lessons that we covered about mole concept. Is that okay? All right. Let me switch and show you a different video, still about mole concept. See, hopefully. Now, after understanding a mole, we can use, let's first play this and see where it goes. Okay, that one also still explains the same thing you've seen. But after looking at moles, you can always look at how we can use moles to calculate different calculations using chemistry. These are called volumetric calculations. Let's see this and try to remind ourselves on these calculations.
We're going to be looking at this equation here, which links the number of moles of an aqueous substance to its concentration and its volume. And you need to remember that we measure volume in decimeters cubed and concentration in moles per decimeter cubed, which we normally write as mole, so MOL, and then a slash decimeters cubed, because this forward slash means per. You might also sometimes see the formula written like this, with N for moles, C for concentration, and V for volume.
Now, Emily, I'm sure when you were calculating this back in O-level, we used to use the first principles, not so? The first principles are great, but for you to easily understand mole concept, we can always utilize these formulas. So that's why even when you will see the videos that in the classes that we had previously, you'll find out that we're using this triangle a lot, the triangle that you see on your screen. That triangle helps us to understand where everything is coming from, not just using cramming first principles. In most cases, we have crammed first principles. And when it comes to questions that are set in objectives in paper one, most people fail them because they don't understand exactly where the numbers are coming from. Why are you multiplying by 1,000? Why are you dividing by 1,000? Or things like that. So here, when you use this formula, it becomes a little bit easier. You understand where everything is coming from, okay? So pay attention to the units. Pay attention to the units of the volume, if it is centimeters cubed or if it is decimeters cubed, okay? For the concentration, it will always be moles per decimeters cubed. And that is key to understand why we introduce 1,000 somewhere, as we shall see in the near future, okay? All right.
So if we had 800 centimeters cubed of sodium hydroxide at a concentration of 0.2 moles per decimeter cubed, then to find out how many moles we had in total, we would just divide our volume by 1,000 to make it 0.8 decimeters cubed, and then do volume times concentration.
So as you can see here, this is what I was talking about. Here in the question we have been given volume in centimeters cubed. But look at our concentration. Our concentration is always going to be moles per decimeters cubed. Now, mathematically, you can't start calculating or using numbers with different units, okay? So we have to convert our volume into decimeters cubed, and that we do by dividing by 1,000. Now, in many cases, people don't really divide the volume first, okay? They just go ahead and say concentration multiplied by volume divided by 1,000, and your mind gets puzzled. Where is the 1,000 coming from? So now you can see here the 1,000 is coming from, it is coming from dividing our volume, it is right there, dividing it by 1,000 to convert it to decimeters cubed. That's where it comes from. And it's important to note that. It's important for you to understand that concept. It was very, very hard for people to understand it in O level. Even the senior threes that I've taught more concept recently, these puzzled them. Why is 1,000 coming from? Where is it coming from? Why do we multiply by it? Why do we divide by it? So now here we are dividing by 1,000. We shall see another scenario where we are multiplying by 1,000 to turn volume into cubic centimeters. So this is important to note or to understand. Emily, do you get that? Okay. Did you type something or did you say something? Emily, are you getting what I'm saying?
Yes, I'm getting.
Yeah, okay, because I wasn't hearing you well. I'm sure Iranya remembers this, not so? Iranya, do you remember where the 1,000 was coming from and all that?
Yes. I've even got the answer.
Hey, okay, that's nice. So, so that's the concept that I wanted you to pick up there to make sure that you understand where the 1,000 is always gonna come from. So the rest becomes simple.
So 0.8 times 0.2, which gives us 0.16 moles.
Iranya, was that your answer? Iranya, was that your answer? Did you get it correct?
Yes, it was.
Okay, good.
Excuse me, sir.
Yes, please.
What is that? Like, if the concentration of sodium hydroxide was 800 decimeters, would we divide by 1,000?
That's a very good question. If the volume was in decimeters, would we divide by 1,000? Absolutely not. Okay. When we have already converted the volume into decimeters, there's no need of dividing it. Right? This is why here we have just multiplied directly to get our moles. Okay. It's the same thing here. In this very scenario here, your question can be answered by this. Have we divided by 1,000 here for a second time? No, because we already have our volume in decimeters cubed. Okay. Originally, we divided by 1,000 because we had our volume in centimeters cubed. Does that make sense?
Yes, it does.
So when we have our volume already in decimeters cubed, there is no need for you to divide by 1,000. If it is in centimeters cubed and you're finding moles, you have to divide by 1,000 to turn the volume into decimeters cubed. Does that make sense?
Yes, teacher.
Okay, let's continue and see.
Or for another one, let's imagine that we have 1.5 decimeters cubed of hydrochloric acid. And we're told that it contains 0.6 moles of hydrochloric acid. What must the concentration be?
Okay, so in this case, Emily, what do? We have our volume, it's in decimeters cubed, okay? And then we have our moles, we are finding concentration. Remember, this triangle is right here. The triangle gives us the formula, okay? For example, if you're looking for concentration, you cover concentration. Once you cover concentration, what remains is your formula. So here we have the moles divided by volume. That will be our formula, right?
Yes.
So what do we substitute in here? What would be your answer?
Okay. Yes. Pass me the card. .4 more. Yes, 0.4 moles per decimeter.
0.4 moles per decimeters cubed. Okay, that's a good calculation. Let's see what we get here.
Well, if we look at our equation, concentration is moles divided by volume. And as they're both already in the right units, we just do 0.6 divided by 1.5, which gives us a concentration of 0.4 moles per decimeter cubed.
So Emily, that is correct, okay, as you can see. And you have also seen, again, the question that you asked prior, that if the volume is given decimeters, should we still divide by 1,000? Have we divided by 1,000 here? No, right? So again, that helps us answer the other question. So good job there.
Thank you, sir.
Now, a more complicated scenario is when we're given an equation like this one here, and we're asked to find an unknown concentration or volume. For example, if we knew that 30 centimeters cubed of 0.5 mole per decimeter cubed potassium hydroxide reacted completely with 25 centimeters cubed of sulfuric acid, we should be able to work out the concentration of the sulfuric acid. Before we do anything else though, it's worth writing out clearly what we already know from the question. For the potassium hydroxide, its volume is 30 centimeters cubed, and its concentration is 0.5 moles per decimeter cubed. And for the sulfuric acid, we know its volume is 25 centimeters cubed. Then, because this is a chemistry calculation, we know that we're going to need all of our volumes in decimeters cubed and not centimeters cubed. We divide 30 by 1000 to get 0.03 decimeters cubed, and 25 by 1000 to get 0.025 decimeters cubed. Now, the basic idea with all of these types of questions is first to work out how many moles of the known substance we have. Then second, use the molar ratio to work out how many moles of the unknown substance we have. And finally, use that number of moles to work out the concentration of the unknown substance. So our first step is to calculate how many moles of potassium hydroxide we have.
So as you can see here, this is now a little bit more complicated, but Irania knows this because we covered it. Now, Emily, here, what we have is a equation that involves mole ratio. It is a reaction, a neutralization reaction between an acid and an alkaline. Okay, potassium hydroxide and sulfuric acid. We know the concentration of potassium hydroxide and we know its volume too. But we only know one thing about sulfuric acid, which is its volume, and we are tasked to calculate its concentration. What you do, first find the number of moles of potassium hydroxide that reacted. Okay, and how do we do that? This one we have covered, finding the number of moles of potassium hydroxide. So calculate this, Emily, and you tell me. Irania, you can also calculate. Have you got the answer? Moles of potassium hydroxide? Emil, have you got the answer? You just have to substitute in here. We already have what we are looking for is the moles, so you cover moles. You have the concentration of sodium hydroxide and you have its volume. So the formula would be that, just multiplication. Emil, have you got it? Irani, have you got the answer? You?
Yes,
What is your answer?
it's 0.015 moles.
Okay, 0.015 moles. Kwagala, do you have the same answer? Kwagala, we can't hear you. I don't know if your volume is unmuted or muted. We can't hear you well. So, after finding the moles, it is true that there will be 0.015 moles.
which we can do by multiplying its concentration by its volume. So we do 0.5 times 0.03, meaning we have 0.015 moles of potassium hydroxide. Then for our second step, we need to find the molar ratio between potassium hydroxide and sulfuric acid, which we can do by looking at the numbers in front of each of them. And remember that if there isn't a number before the substance, like for the sulfuric acid, then we just read it as a 1. So the molar ratio here is 2 to 1, which just means that for every 2 moles of potassium hydroxide, we'll have 1 mole of sulfuric acid. So because we just worked out that we have 0.015 moles of potassium hydroxide, we're going to have to divide that by 2 to find out how many moles of sulfuric acid it reacted with, giving us 0.0075 moles of sulfuric acid.
Okay, so now that we have, using the mole ratio, we have the moles of sulfuric acid. The way we use mole ratio is just using the balancing numbers, okay? Here we see that to balance the equation, we had to put a 2 on potassium hydroxide and then a 1 on sulfuric acid. So meaning that 2 to 1 was our mole ratio, which means that 2 moles of potassium hydroxide will react with only 1 mole of sulfuric acid. Meaning for us to get the moles of sulfuric acid, we have to halve or divide by 2 the moles of potassium hydroxide, which gives us 0.075 moles. Okay, so now we have the moles of sulfuric acid that reacted. How do we find the concentration? Okay, remember our formula is right there. We have now the moles of sulfuric acid, we have its volume, we need its concentration. All you need to do is cover concentration. Okay, once you cover concentration, you have your formula, right? So what is the concentration of sulfuric acid that we use to react? Can you calculate that? When you're done, you let me know. Rania, have you got the answer?
It's 0.001875 decimeter cube.
Okay. Is that the concentration?
Yes.
Are you sure? All right, let's see the answer. Let's see if you got it right.
And finally, we can move on to our third step, which is where
Okay.
we actually calculate the concentration using the number of moles that we just found and the volume that we were given in the question, which remember we converted here to 0.025 decimeters cubed. So we take our 0.0075 moles of sulfuric acid and divide it by the volume of 0.025, which tells us that the concentration of sulfuric acid is 0.3 moles per decimeter.
Do you see the answer, Irania? What did you do wrong? This is why I asked you if you were sure. So tell me, what did you do wrong there?
Instead of dividing, I multiplied.
Yeah, you see? So you have to cover here. When you cover concentration, what remains is moles over volume, okay?
Yeah.
We only multiply when we are dealing with the lower ones, eh? The lower ones, concentration and volume. You understand that?
Yes.
When it is up and down, that is division. For example, if we covered, let's say, let me first remove this. If we covered volume, meaning we are looking for volume, it would mean moles over concentration. Does that make sense?
Yeah.
Hey. And if we covered moles, let's say we are looking for moles, what you're looking for is what you cover. We'll have concentration times volume. This is multiplication. Yes, concentration times volume. Right?
Okay. Yeah.
So that's the trick.
Okay, I've got it now.
Okay, good. So yes, that's it for this video. This video was helping us remember these volumetric calculations. Let's watch one more to see if we can get other examples. Then
Okay.
we can wait for the
meter cubed. And that is our final
website
answer
to
to the
be
question.
more responsive, and then we can do those exercises. Okay. So the other one is here.
We will look at 2 different examples together, and then one for you to try out yourself. These calculations enable us to work out the actual concentration.
Can you hear very well? Is the volume clear? Emily, you had disappeared. I don't know where you had gone. Iranya, what's the network? Sorry. Iranya, can you hear very well?
Yeah, I'm getting it.
Okay, so Kwagala, we have just finished the other calculation, but pay attention here and you pick up something, okay?
Yes, sir.
All right.
concentration of an unknown solution. So let's look at an example. We have carried out a titration. We started with 25 cubic centimeters of an unknown solution in the conical flask. We then added 20 cubic centimeters of the known solution of concentration 0.5 mole per cubic decimeter to complete the reaction. What is the concentration of the unknown solution? First, we need to convert volumes to cubic decimeters. We do this by dividing by 1000. So 25 cubic centimeters divided by 1000 equals 0.025 cubic decimeters. And 20 cubic centimeters divided by 1000 equals 0.02 cubic decimeters. Now you need to work out the number of moles for the known solution, because we already know the concentration and volume for this. The number of moles equals concentration multiplied by volume. So in this case, for the known solution, the number of moles equals 0.5 multiplied by 0.02, which equals 0.01 mole.
So this one we have looked at, okay? We're just trying to find the moles for the known solution, the solution that we were titrating with, okay? It's given in the equation that 25 centimeters of an unknown solution reacts with 20 centimeters of 0.5 molar known solution, okay? We're just using known and unknown. So we have the concentration of the known solution and its volume right there. We convert the volume first to get 0.02 decimeters cubed, which is right here. And then we use our formula where we cover moles. If you still have the triangle drawn somewhere there, you know that when you cover moles, you remain with the ones below, concentration times volume. Here, we already have this to give us 0.1 moles. So now we have the moles of the known solution, okay?
Using this, we can now calculate the unknown concentration. The concentration of the unknown solution equals its moles divided by volume, which equals 0.01 divided by 0.025, which equals 0.04 moles per cubic decimeter.
So here we're assuming that the reaction was in the ratio of 1 to 1, okay? It is why we have the same concentration for the known right there with that of the unknown, okay? So same moles, same number of moles, meaning the reaction ratio was 1 to 1, okay? So here in the unknown, we are looking for its concentration, which gives us moles divided by volume. Already we were given its volume and we converted it already, okay? So here we just divide and there is your answer, 0.04 moles per decimeters cubed. That is the trick behind. Is there anything confusing there?
So the unknown solution was at a concentration of 0.04 mole per cubic decimeter. It is much easier to take the time to understand what is happening, but if you prefer to just learn an equation, this is all you will need to know for titration calculations. Using the values we've just determined, we can make use of the following formula. The concentration of the unknown solution equals the concentration of the known solution multiplied by the volume of the known solution divided by the volume of the unknown solution. So, the unknown concentration equals 0.5 multiplied by 20 over 25, which equals 0.4. But you may not pick up all the marks in the test or an exam using this formula because it doesn't show your understanding. Sometimes you need to work out the proportions involved in the reaction by looking at the equation for the reaction. So if we had this question, the balanced equation would look like this. So 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. We are now ready to do the calculations. Convert the volumes to cubic decimeters. 20 cubic centimeters divided by 1.
So this one is similar, this question is similar to the one that we have worked out previously in the other video. So here, the advantage is we have the equation which is below here, all right? And we see the mole ratio is 2 to to 1, just like in the other video. In the question, we have been given the volume of sulfuric acid and the volume of sodium hydroxide and its concentration, right? And now they want you to find the concentration of the sulfuric acid, which is the unknown right now, okay? So again, you just have to find the moles of sodium hydroxide. Can we find the moles of sodium hydroxide here? Calculate them and let me know. You have volume of sodium hydroxide. You have also its concentration. Remember to convert, okay? Remember to convert into decimeters cubed. So tell me the concentration of sodium, the moles of sodium hydroxide. Emily's network is disturbing. She has disappeared again. Irani, have you found the moles of sodium hydroxide? Remember, cover moles, what you remain with, it will be concentration times volume. Emily, you're back, but you're not back with audio. So make sure you join with your audio. Can click somewhere there on the, I don't know if it is the left, I don't know if you're using a phone or computer. And join with your audio. So we are calculating the moles of sodium hydroxide here. We have the volume, 20 cubic centimeters, which we can convert into decimeters cubed by dividing by 1,000. And then we have its concentration. The concentration is also given here, 0.5 moles per decimeters cubed.
I got 0.01 moles.
0.01 moles. Okay, that's good. Emily, have you got any answer yet? Your audio is off.
1000 equals 0.02 cubic decimeters. 40 cubic centimeters divided by 1000 equals 0.04 cubic decimeters. Now calculate the moles for the known solution, sodium hydroxide. The number of moles for sodium hydroxide equals 0.5 multiplied by 0.02, which equals 0.01 mole.
So, Iranya, that was your answer, right?
Yes, sir, it was.
Okay, good. Now you've got this.
Now calculate the concentration of the unknown solution. The concentration of the unknown solution, sulfuric acid, equals 0.01 divided by 0.04, which equals 0.25 mole per cubic decimeter. But from the equation, we know that 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. So 0.25 is for 2 moles because we have so far assumed a 1-to-1 ratio. So we need to divide this by 2 to get 1 mole of sulfuric acid. So 0.25 divided by 2 is 0.125. Now here's a question you can try out on your own. Pause the video, work out the answer.
Okay. So right here, one thing that you have to note about mole ratio, we looked at it in the other video, is that you don't have to first calculate the entire concentration and then divide by 2. You can get this number of moles of salt after calculating them, of their known. You get them, then you divide by 2 due to the mole ratio. Depends on what mole ratio you have. Here we have 2, okay, meaning that 2 moles of sodium hydroxide will react with 1 mole of sulfuric acid. Okay, so when you get this, you half it or you divide by 2, you get the moles of sulfuric acid that reacted. It is those moles that you will divide by 0.04, which is the volume. The answer you get will be the final answer there. Okay.
So 0.25 divided by 2 is 0.125. Now here's a question you can try out on your own. Pause the video.
Okay. So try out this question and see. You have, just write it down and then you'll try it out and let me know what the answer is. You can submit the answer in the what? Submit the answer in the messages in our website. You can use WhatsApp if the website is still disturbing. So write down this question quickly. Emily and Iranya, write it down, eh?
Okay.
All right. You have 1 minute, write it down and we conclude. You have 25 cubic centimeters of barium hydroxide and 25 cubic centimeters of 0.6 moles per decimeter cubed hydrochloric acid. Given the balanced equation below, what is the concentration of barium hydroxide? Write the equation to remember. Are you done? Emily, are you done? I see your back.
I'm done.
Okay, what about you, Rania? Are you done writing it?
Yes.
Okay, good. I am sure now you are well conversant with how to submit this type of assignments. So you can write in your book, take a picture and upload it in form of a message in the website where you access your units. Okay?
Okay.
You'll search my name, Teacher Solomon. Just type in Solomon to bring for you my name, and then you send me a message while you have attached your picture or PDF or whatever.
Okay.
Okay? Is that okay, Emily, also? All right. So if it is okay, then that's good. We'll stop here for today. That was a good revision of mole concept. Make sure you go through the units. Let me know what you want to learn. Let me know what is disturbing you most, and we shall cover that. Okay, remember this is self-paced, so whatever you tell me to cover, we shall concentrate on that. So go through the units we have on the website. Tell me what is bothering you. We go through that quickly.
Okay, thank you, sir.
You're welcome. See you soon. Well done. Emily, sorry about your internet. Hi.